Hi, I'm Haoyu Wang. I'm from the University of Pennsylvania. The work I'm going to present today is a joint work with Dr. Kulkarni from Stanford University and Professor William Wang from University of California, Santa Barbara. In this work, we propose a new paradigm for learning knowledge graph embeddings, which are deep and contextualized. Inspired by recent advances in learning word representations from deep neural language models, we derive connections between language models and random walks on knowledge graphs. As noted by Perosi et al. In 2014, there exists a similar power law distribution between vertices in knowledge graphs and words that appear in natural language. By leveraging these connections, we learn rich knowledge graph embeddings that are both deep and contextualized. We represent a knowledge graph not as a collection of triples, but as a collection of entity relation chains. A BiLSTM accepts these chains as input, and functions of the internal states of the BiLSTM are considered to be the embeddings of entities and relations. Here is a visualization of the contextualized embeddings we've got from Dolores. The figure on the left shows the entity embeddings with the context of relation people, place, lived. We see that Beethoven and Brahms, though Germans, ever lived in Vienna, and their embeddings lie in between other musicians who were Germans and Austrians. The figure on the right shows the cluster of the embeddings with the context of relation people nationality. Conventionally, if we use trans E and trans D, the philosophers, playwrights, and musicians would form three different clusters by themselves. However, in Dolores, with their nationality, the Germans, Austrians, and British people form their own clusters, regardless of their main occupations. Our method consists of two main components. The first one is called path generator. This component is responsible for generating a large set of entity relation chains that reflect the varying contextual usages of entities and relations in the knowledge graph. We use P and Q to respectively control the properties of random walks. We generate 20 chains for each node, and the length of each chain is 21. The second component, Dolores Learner, is a deep contextualized model that takes entity relation chains as input and learns entity and relation embeddings, which are weighted linear combination of internal states of the model, thus capturing context dependency. As can be seen from the figure, we input a pair of entity and relation at one time and split the vectors from internal layers to get the contextualized embeddings for entities and relations. Given a downstream model, which is not necessarily the pre-trained LSTM, Dolores learns a weighted linear combination to yield a single vector for usage in the embedding layer of the downstream tasks. While it is obvious that our embeddings can be used as features for new predictive models, it is quite easy to incorporate our learned Dolores into existing predictive models on knowledge graphs. The only requirement is that the model accepts as input an embedding layer. If a model fulfills this requirement, we can just use Dolores as a drop-in replacement by initializing the corresponding embedding layer with Dolores. In the evaluation tasks, we show that we can improve several neural models on various tasks by incorporating Dolores as a drop-in replacement to the original embedding layer. In conclusion, we present a new method of learning deep contextualized knowledge graph embeddings using a deep neural sequential model capturing both context-independent and context-dependent cues. We show empirically that Dolores can be easily incorporated into existing models in KG to advance the performances on several tasks. That is all. Thanks for your listening.